In this module, I will start with an intriguing question and we will see how far the literature has gone. It has a long history. The subject matter is itself almost 70 years old. So you will see what is coming up here. There are some basic results, then some research problems. Altogether, it's quite revealing and interesting. Okay. Shubhro, did you ever wonder what if capital N, I mean the size of the finite population, is itself in question? Usually, in the context of household surveys or in other aspects of survey, we assume that the total number of households is known. So when we discuss about household surveys and various aspects of the household survey, such as income or expenditure, we do not feel about the question of getting to the size of the finite population, nor we do doubt about the exact size of the population. We take it for granted that we know how many households are there under the purview of the survey. We always assume that the population is perfectly known, that all the households have been labeled, and that there is a finite labeled population of size capital N. We never question about the value of capital N. Simply said, it is a finite labeled population of capital N units, and the moment we say labeled, the units are marked 1, 2, 3, etc. up to capital N. There are of course other scenarios, fish population in a lake, wildlife population in a forest and the like. Here the total number is presumably unknown and estimation of the exact size capital N is by itself an intriguing question to deal with. I want to give you a taste of the methodology adopted in such cases. Note that we are referring to unbiased estimation of capital N. This word unbiased is very intriguing and interesting, and that leads to so many research problems and research methodologies. Without the word unbiased, we would have felt very comfortable. Statistician would apply some judgment and give something, and you don't have to justify because you don't want unbiased estimate. The moment you talk about unbiasedness, all the questions come up. You have to understand the probability model, computation, verification, etc. It's a big if to ascertain that the estimate is unbiased. We tacitly assume that sampling at random is still possible from among the units in the population. This subject matter, as I said, is quite old. It has been studied quite extensively. Still the researchers find it open problems now and then. That is the beauty of research. You read through the literature, you find so many results, still you are not satisfied, you feel something more could be done, this assumption could be dropped, that type of generalization could be made, and so on. That is the beauty of research, as a matter of fact.
Sir, I thought unless we know the population size capital N and the identity of all the population units in a unique manner, that is, in a one-to-one basis, we cannot consult the random number tables and go about random selection of units. Strictly speaking, also from the point of view of operation. Is that not correct?
Well, let's see. Suppose you have a box containing an unknown number of balls. What if I ask you to randomly select 5 balls? Can you do that?
Yes, sir. I will shuffle and reshuffle the balls in the box repeatedly till I feel sure that the balls have been thoroughly mixed. Then I will ask someone with folded eyes to put his or her hand inside the box and pick up the balls one by one, and up to 5. That's it. I'm sure, for all practical purposes, I've adopted simple random sampling without replacement, with n unknown and small n equaling 5. That's true, very true. No need to know how many are there, yes? That's true, yes.
In case of fish population in a lake, the particular method adopted is known as capture-recapture method, and there are various versions of it. Simplest version goes like this. In step number 1, you go for a catch of initial size called small m. You mark them and release in the lake. Marking goes like, as you know, when you go for casting our vote, there is a black spot given at the fourth finger. somewhere so that it stays permanent. That's what you do. You just go for you call a fisherman, then you go for a catch in the lake, and then you get some catch. Let there be the size small m. Immediately give them red marks and release them in the lake. That's the whole idea of marking. This is a non-random catch. It was not a random catch. You just go there and get a catch of an arbitrary size. But marking separates this lot from the otherwise free or unmarked fish population in the lake. The moment you make a first catch, you mark them and release. Now you know that in the whole lake there is a separation among the artificially you have created a separation, a marking, and marked and unmarked fish in the population. Let there be a time gap to make sure that all the fish are sufficiently and thoroughly mixed inside the lake. Now you make a random catch of size little m and check how many of these are marked. If this number is k, which is of course random, then the sample proportion of marked fish is k over little m, whereas in the population the proportion of marked fish is small m over capital N, because small m was initially marked. Therefore, you can apply the method of moments. You can develop the estimating equation k over n equal to m over capital N, whence you get the estimate of capital N as m into n over k. This should serve as a reasonable estimate of capital N. Note that we are not talking about unbiased at this moment, but this should serve as a reasonable estimate of capital N, except that there is a possibility of k being 0. And if k is 0, then this whole thing is gone, but that gives a message that initially you had marked small m. In a random sample of little n, you don't get anything. That's because capital N is presumably very, very high. So you get a message about the size of capital N. Not exact value, but you got a message. So that is definitely, it is not desirable that we end up with k equal to 0 and we feel comfortable with the message only. We have to have something in hand. If that happens, that k equal to 0, one can still do something about changing m into n by k to another formula. Those are given in the literature. But as I said, you got the message that capital N is substantially large.
As a compromise, can't we replace k equals 0 by k equals half, at least to avoid this situation? Of course, we may change n to n plus half, or else we may continue to sample more fish, go for a second catch, etc. I don't know, there are options, I guess so.
You see how from a very simple catch-the-catch method, ideas are emerging. This method indicates a mode of separation of the population units into two groups, as I said, marked and unmarked. And we are basically going for success count towards estimation of capital N. Success count means marked. So note that the estimator capital N hat, mn over k, that is biased, that even when k is positive, because k is a random variable and it is in the denominator, that's always a problem. So what about a variation of the above method for unbiased estimation of capital N? So there was a time, I am talking about in the 50s. In the 50s, people talked about the capital method. They could soon realize that the estimate of capital N is not always applicable. Even if you apply it, it is not strictly unbiased. Then people started looking for unbiased estimation methods, and those are there. So let me cite one such method here. The step number 1 is the marking and releasing. You do the same thing as before. You make a catch, you get m fish, you mark them and release in the population. Since the population m are marked and capital N minus m are unmarked. Step 2 says you recatch fish from the table, from the lake, you recatch one by one and at random and with placement. Pick up one and then give it back, pick up one and give it back, pick up next, give it back, and so on. How long do you continue? You continue doing this thing, and every time you pick up one, you check if it is marked or not. Whether it is marked or not, you are always putting it back, but in the process you are making a count of the marked fish. So you continue doing this till marked fish are caught a pre-assigned number of times, say k. So that is the idea. This reminds you of the inverse sampling method. Earlier one was direct sampling, this is inverse sampling. So you continue taking one by one at random and with replacement till you get marked fish, till that marked fish is got so many times a pre-assigned number k times. Now in the process, suppose sk is the number of trials required to achieve this feat.
Sir, we know that the number of trials, sk, is negative binomial with success probability p equals small m over big N. And hence, its expectation is k over p, which is k times big N divided by small m. And hence, it looks like n is equal to m times...
You mean the estimate of n?
So the estimate of n is m times sk divided by k, and this serves as an unbiased estimator for capital N. I believe we can also compute variance of n hat without much problem. This, I think, is n times n minus small m divided by small k. I think I'm right. Thank you, sir, for discussing this interesting problem and the basic sampling and inference methods. I'm sure there is so much more to it.
Yes. So as you rightly said, this time capital N hat m sk over k is indeed an unbiased estimator because sk is the random variable and that is coming in the numerator, so you have no problem in computing its expectation. Likewise, we can work out the variance of sk, and that is what comes in the expression for variance of n hat. And because it is a negative binomial distribution, we know all moments, etc. So it's very easy task to compute the mean and variance of sk, and that is indeed what we have done here. Okay. So, but as I said, this is only a very basic technique, but there are many variations of this technique that have been made available to the practitioners. There are a lot more in terms of the nature of the units in the finite population, also the methods to be adopted for ascertaining the size of the population. Note that unbiasedness may at times create problems, so one has to think even otherwise more logical and sensible estimators after generating data. It is not always advisable that you run after unbiased estimates. It may be very difficult unless you really start with a reasonably good sampling procedure. Not all sampling procedures are amenable to construction of unbiased estimators. Things may be difficult, as it happened with the capture-recapture method itself. So you have to do some modification. Like that, there are many ways of resolving the sampling problem, or even if we start with standard sampling problems, we may think of more logical and sensible estimators after generating the data than running after unbiased estimators. Anyway, let me stop here. We will take up some questions, and in this module we introduced what is known as capture-recapture technique or capture-recapture method. The idea is to estimate the size of the finite population itself. This is an intriguing question, but this question makes sense in some non-standard, when we are dealing with some non-standard finite populations, even though we know that the finite population, it is in fact a finite population, but the question of leveling the units 1, 2, 3 up to capital N, that question is vague because that capital N itself is not known. Even if somehow we have an idea about capital N, there is no question of going for identifying the units one by one. And the classical examples are the lake population in a lake, or the wildlife in a forest, etc. So in those cases, we need special techniques to estimate the size of the population, and this technique called capture-recapture method and its modifications over all these years. The technique is itself almost 70 years old, and then there are ample modifications and diversions and extensions of this method. So in this module, we just started with the very basic idea about the capture-recapture method and how estimators can be proposed and how estimators may turn out to be biased, and then how to modify the estimators and the methods to be able to sort out some kind of unbiased estimators. So this is just a modest beginning of a huge area of research. Research continues even now. So we will take up now some exercises and MCQs. In the broad framework of finite population of size capital N, presumably unknown, we are referring to the capture-recapture method and its modification. We have learned little bit about it. Let us take up some questions here. So question number 1 reads like, for estimation of the size of a finite population, suppose some of the population units have already been identified, and these are capital N sub 0 in number. It is also possible to separate them from the rest of the population units. Very good. Under this scenario, develop your sampling scheme and provide an estimate of capital N. The moment it says that some of the population units have been identified and it is possible to separate them out, so we better take them away. That number is, head count is already known, capital N. If we look to the leftover population, treat it as a population in its own right, apply our technique of this capture-recapture, straightforward, or the negative binomial version of capture-recapture, but we apply it only to the remaining part of the population, because this part has already been identified and it can be separated out. So this is a straightforward question. We refer to estimation of the size of the curtailed population. The size is capital N minus N0. And once we have an estimate, to that we add N0 to come up with an estimate of the size of the total population. And the fact that the estimate of the size of the total population, entire population capital N, should be at least capital N0, the part which has already been identified, that is also taken care of in the process of separating and then adding. So apparently there is no conflict, and this question can be resolved without any difficulty. Let's read question number 2. Please read it.
In the framework of question 1, suppose it is not possible to separate the identifiable units and from the rest of the population. How would you proceed towards unbiased estimation of capital N?
This is a very good question. It is a very difficult question. The difficulty level is quite high. It says you are not able to, you know that there are so many units which you have already identified. Imagine 25 units are there which you have already been able to identify, but you cannot separate them out. You know, what does it mean? The population has at least 25 units. If capital N0 is 25, you know the existence of 25 units in the population. So capital N is at least 25. But unlike in question number 1, you are not able to separate them out and put them back, put them elsewhere. They are mixed here. Now how do you proceed towards unbiased estimation of capital N? Whatever formula you use, there is no guarantee that an estimate of capital N will be at least capital N0. That guarantee you don't have in this setup. So you have to really think how to ensure that capital N hat is greater than equal to N0. You could as well ignore this information and go ahead with the usual method of capture-recapture or the modified using this negative binomial approach. You could do that. But then you already know that there is a point mentioned here that capital N is at least N0 and that number N0 is known. How to ensure that and at the same time come up with an unbiased estimator. That's a good problem, okay? What is the next one, please?
Argue that under steps 1 and 2, simple random sampling with replacement, the random quantity Sk follows a negative binomial distribution with success probability m over capital N and parameter k.
Yeah. So the fact that we have used in the text, we just made a statement there. Sk follows negative binomial and therefore etc. etc. That is the thing that they want you to prove here, okay? But you know, this is a standard probability problem involving negative binomial distribution. So this is almost everybody knows. You should know how to handle this problem. What is the next one?
Argue that under the steps 1 and modified 2, simple random sampling without replacement, the random quantity Sk follows negative hypergeometric distribution with initial success probability small m over capital N and parameter k. Compute the expectation of Sk and use it to suggest an unbiased estimator of capital N.
Yeah, this is a non-trivial problem. I can refer to a textbook where you will get it, but you better think on it yourself. I can read the problem again. Step number 1 means you have an initial catch of little m, those are marked and released. Earlier step number 2 was referring to with replacement sampling. You go on picking up units after they have been released in the original population, they have merged with the original population. You go on picking units one by one with replacement till a pre-assigned number, namely m, of the unit, and m marked units are encountered m times. That was the idea. And in the process you knew that the number of attempts needed, that follows negative binomial distribution, etc., etc. As against that, this time you are told that after the step 1, namely picking up m and then marking them and releasing in the population, next time you are referring to one by one drawing and without replacement. So you are drawing one by one and you are keeping it aside no matter whether it is marked or not. And when do you stop? You stop when you get exactly m marked out of, exactly k marked out of m. M is the initial number marked and released. You go on picking up one by one without replacement till you get m marked. So that is till you get k marked. That is the question here. So this time Sk, it follows what is called a negative hypergeometric distribution because it is tagged to without replacement sampling. It's a very good problem, standard probability problem, distributional problem, and then you know initial success probability is m by n. That's because m is the number marked, but the moment you get a failure, you know how it is tending because of without replacement. The moment you get a success, you know how it is tending because it is without replacement. So every time there is a tricky thing coming up, and then you have to compute expected value of Sk because you want to continue till you get k marked. It's a good problem. I won't tell the answer, but you should be able to get it. And then there are standard books. You all know that this Johnson cause, that is the Bible in the study of distributions. In that book you will get negative hypergeometric distribution, mean variance computation, etc. So it is good to think on this problem independently, and if you really need, you can consult Johnson cause book. Okay, that's how we stop now. I did not feel like putting any MCQs here because these are special topics. You need to learn slowly. There are not too many textbooks dealing with these topics. I don't even know of any single textbook which deals with this topic, even though this capture-recapture method is there, but that's not readily available in any sampling textbook. That's the problem. Okay? So I did not feel like giving any MCQ in this context. 4 questions are good enough. If the teachers take up this thing, they can, I'm sure they can give you some more questions, more references, and I don't know of any standard textbook where these things are being discussed. I'll stop now.